It's the time of the year to get together. Sadly this time around virtually. Let's make the most of it, we always do. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this so long. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's take our time to gather all the knowledge. Brilliant speakers, we share it just with you. Collaborations, friendships, and so much more. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this for 2 years. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's get to it, it's gonna be fun. ICPS. Hooray!
Hello everyone, and welcome to this workshop in How to Science Show. The next half an hour, 45 minutes, we will be doing some physics experiments and talking about why it works in front of an audience. So this is not going to be plain physics show. I will be discussing why I'm doing stuff, while I do it and after I do it. And we will also have a small debate in the chat function here on YouTube. So if you have any questions, just write them down and I will get them told right away. And then we can have a discussion about what is going on. A little bit about myself. You probably recognize me as a member of the OC, but when I'm not OCing and when I'm not physics studying, then I am a member of the Science Playroom. We are making science shows and we are hosting workshops here at NBI, the Niels Bohr Institute, for high school students. Besides that, I myself have a small company where I host talks and lectures and speak about science dissemination. How to do science talks for the public. So that is what we're going to do. The level of this talk will be for high school students. So this talk is not for the physics. This is for how to talk about physics. So the first thing I want to show you, the first experiment and the first little story will be about this. This is a dewar, meaning a giant thermos for liquid nitrogen. So it's always a good idea to tell some story to get the audience on your side. So this is the experience they usually get. When I'm not studying here, I have a small company where I drive out and decorate for children's birthdays. But sometimes I'm in a real rush. So when I get out there, I need to blow up a lot of balloons in a very short while. And doing this many times takes too long. So what I chose to do was rent a van and then just blow up a lot of balloons before going out. But then I just had a huge van full of balloons. And that didn't really work because I needed all my other stuff for the decorating as well. So what I found out, what I did, was I had this magic containment unit for balloons. So I just took them like this. And I blew them up. And I will continue doing that. And then in a very short while, I had all the balloons ready for the decorating every single time I got out. So no need for a huge van and no need for scrambling with blowing up all these balloons. They could do it themselves. So that's the beginning of my typical science talk. This is a way of introducing myself to the audience This is a way of saying this is going to be slightly silly, but filled up with all sorts of sciencey things. So the next thing that I'm going to do is try to explain what we just saw. This is a ladle of the liquid nitrogen. So first of all, if I have a very small audience, I will go around and letting them see this ladle up close so they can see the bubbling effect of the boiling nitrogen. And if I have a larger audience, I will take it up close to myself and blow on it a little bit. Just to show them these clouds of nitrogen coming out. And then I'll make a poll. It's always a very good way to interact with your audience to make them answer something. So I will say, can I stick my fingers down in it? And depending on my audience, if it's children, they will say, no, don't do it, you'll freeze your fingers. And sometimes high school students will be a little bit skeptical. Oh, he probably shouldn't do it. And then there often is 1 or 2 people that know about, yeah, you can do it. And then I pour it over myself. And this often splits the audience in 2. Those that are just dropping their jaw, and those that are going back in kind of awe and panic. What is going on? And then we talk about the science. This is the light and frost effect. So when there is a temperature gradient of around 200 degrees centigrade, then this happens. The liquid never touches my skin. It evaporates very quickly, and we have this small insulating layer of gas between me and the liquid. And then people always say, and I talk with them about, why not use gloves then? But imagine I had gloves up till here, and I spilled my liquid nitrogen here. It will go down the gloves, and my fingertips will freeze. But this light and frost effect makes it possible for me to just, well, handle the nitrogen without having to worry about freeze. So then we can take a rose or a leaf or something from outside. Just pretty much any plant will do. And we talk a little bit about what it is. This is biological matter. It consists of around 70 to 80% water. That's just the same as me. So I'm gonna say this is me. I'm a rose. My hand is a rose, and if I dipped my hand in the liquid nitrogen, this would happen. So first, this is a quite dense rose head, so we need to wait a little bit for a thermal equilibrium. And that's a word only to be used if the audience knows what that is. But all of you being physicists, I can do thermal equilibrium. So there we go. And then this will happen. So that is always a good way to say, please don't dip your hands into liquid nitrogen. And if you have the time and you have the possibility, then play with it a little bit in front of your audience. It doesn't have to be an hour or 30 minutes or whatever long your science show is, straight with show after experiment. Play with it a little bit, have fun. Make the audience feel that you enjoy it as well. And I can tell you, I've done this a million times. And every single time, there's a small boy inside me that giggles. Because being able to crush this biological matter in this way is just awesome. So then there are several different options to go from here. Now we have opened the show. We have played a little bit around with it. We have explained some of the dangers and some of the fun. And then we can go on to talk about the possibilities and the way that liquid nitrogen can improve us. So I'm going to present this. This is a very strong magnet. It has a lifting capability of around 100 kilograms. So that means that if we put this on a good ferromagnetic material like iron, then I can just hang from it. So we place it on the table in a way so we doesn't have phones or watches or anything nearby it. I often, when I do these shows, forget to remove my watch at this time. And I can't count the amount of times I've looked at my watch and said, whoa, this show is just rushing past me. But the magnet pulled the time in my watch, or the little hands moved. So I just made 20 minutes go like that. So that is quite funny for the audience, but not always so nice for your watch. So what we're going to do is take this. This is yttrium barium copper oxide. This is a superconductor I've wrapped in cotton wool and gaffer tape. The cotton wool and the gaffer tape is just there to keep the temperature low for a longer amount of time. And this is a cup. We place the cup on the magnet and the superconductor inside the cup. And then we pour some liquid nitrogen over it. And now we need for it to cool down. That takes time. So you have several options here. You can just look at it. That's boring for everybody involved, so I wouldn't recommend that. So what I usually do here is take the nitrogen and throwing it around a little bit, or pouring it over myself again, or do something a little bit different. Can you switch to that camera over there, please? If you're standing in front of a blackboard, then throwing it onto that always gives quite a good effect, because you can see these clouds forming right away. And back over here. It's very TV kitchen-y. I love it. So you can just see, okay, it's not ready yet. It's still boiling, so it's not cooled down.
There's a question in the meantime.
Yeah, question. Yeah, perfect.
James asked, what's your favorite liquid nitrogen ice cream recipe?
Oh, that's a good question. We have a dessert in Denmark called koldskål, which uses egg. What's it called? The yellow part of the egg in English? Yolks. Yeah, thank you. Yolks. Egg yolks. And then, oh, this is a very good recipe because I don't know the English name for any of the ingredients. Kernemælk.
Buttermilk?
Yeah, buttermilk. Perfect. This is just a Danish discussion we're having right here. So egg yolks and buttermilk whipped up together with vanilla and some sugar, and freezing that. I think that's amazing. Oh yeah, and lemon. Never forget the lemon. And just mix all those ingredients together, and you get a very nice ice cream. I love doing that. Sometimes when I have guests over, I enjoy bringing some liquid nitrogen back home, and then I take a lot of different stuff. I make some real ice cream mixes, so we can do that. But then I have smoothies and I have marshmallows, which we will talk about in a short while. I have this koldskål, which I just told you about. And then often I do some strawberries, which you definitely shouldn't cool down in liquid nitrogen because the water content is very high. So that freezes a lot and you shouldn't eat it when it's frozen. But it's quite fun to do it. So a lot of different liquids that are nice when cold, like soft drinks. Yeah, sometimes actually I bring soda with different kinds of flavors. because the sugar content is so high that it doesn't really freeze to ice. If you mix it really tough while pouring liquid nitrogen over it, you can get this almost sorbet consistency, and that's quite nice. So I enjoy when I'm having liquid nitrogen ice to just freeze a lot of stuff, just to experience it. And I'm always doing different kind of stuff, always something I haven't tried before. So koldskål, the recipe I told you about, perhaps we can get a recipe link in the chat. Then you can try to make it yourselves. That's really nice. Also not frozen, that's a really good dessert. Okay, so what I'm trying to do here, it seems like this superconductor had been dropped on the floor, but I don't think it's pinning that well, but we will try it anyways. So when I'm presenting this, first I hold it up. Then I'm talking about the magnet. I'm saying, do you know magnetic field lines? And we talk about field lines going from one side to the other. We talk about this picture of the Earth with lines going from north to south. And people say, yeah, we've seen that picture. Okay. Then I just pour out the liquid nitrogen. And then I have a superconductor. Yeah, as I imagined, it didn't pin that well. No, it didn't pin that well. So I'll just go to the next step, because this always works. And I can bring it a little bit closer to the camera. Is this a good distance? Yeah, perfect. So when having this flux pinned superconductor, and flux pinning means that the magnetic field lines go through the superconductor and then joins up. So there isn't many field lines, but a few strongly pinned lines going through this superconductor. Then it's stuck in the magnetic field. You can spin it around. You can even remove it and put it back in. And this is always like magic for people. This trick is great because it explains a lot of physics. It explains or makes people wonder, and it's just so nice. I don't know what to say either than this is just really good. And from here we can go in many different directions. We can talk about green energy transfer. We can talk about green transportation, trains with no resistance on the train tracks, and we can talk about improving life in hard to reach places. So there's a lot of green and humanitarian directions you can go from this experiment. So you can take your talk to the next level. You can talk about something other than physics. I quite enjoy doing that because as a rule of thumb, you should move back to something that your audience know every 5th minute. So more than 5 minutes of new things is just not getting processed. So every 5 minutes, return to something that your audience knows. And this is very abstract and very difficult to explain. I often say here, if you can explain it for me, then you win the Nobel Prize. Because exactly how high temperature superconductors like this works on the smallest scale isn't really that well known. So to be able to tell me that is a Nobel Prize. And especially for 9th graders and 1st level of high school people, or 9th graders, as that's a universal standard. That's the final year of our primary school. And then 1st year high schoolers, there are often people there saying, yeah, I know what it is. It's magnets. And then I tell them, yeah, but doesn't magnets usually stick to whatever you hold them at? And then they just look at this floating piece of metal in the air, or ceramic actually, and they're getting quiet. And then we talk about, yeah, but you're right, magnets are an important part of what is happening. And that is always very important when you're doing a show. Never belittle your audience. If they say something that is clearly wrong, don't laugh about it, and don't tell them every single reason why it's wrong. Tell them the one reason that is right. Tell them why that was a good decision or a good explanation, even though it wasn't. So magnets in this is not the best. Wait, now it's too warm. So magnets for this explanation is only a very, very small part of the story. But say, yeah, magnets, that's right, magnetic field lines. But from there, you can then further the explanation. So always say yes to what your audience is saying and explain it from their point of view. Because you need to remember, doing a talk is not for your sake, it's for their sake. And then liquid nitrogen is just an amazing play tool. You can do a lot of different stuff. When I do this for just high school classes or primary school classes, then there isn't that big of an audience. So after the talk, I offer them some marshmallows. But during the talk, I show them what I'm talking about. Because we have now said that liquid nitrogen is very cold and it's dangerous. You shouldn't play with it if you don't know what you're doing. And then we drop some food into it. And we just show what happens with biological material in this. And then we eat it. Now I need to chew before I can talk again. This breath of dragon smoke is always amazing. And it again splits the audience in two camps. The ones that really want to do it and the ones who hardly can get to it. But doing this makes all of a sudden everything more relatable, because everybody knows a marshmallow. And that is again return to something your audience knows. Okay, I think that was enough play with the liquid nitrogen for now. So we will continue over here. And I've been talking for, 20 minutes already. Wow. Okay. So what we have here is a Rubens tube. It's a 2.5 meter steel tube with small holes in the top. Now we're getting the lights dimmed a little bit because we're going to play with fire. Contrasts are always good. So we just played with really cold stuff. Now we're going to play with really warm stuff. So in one end, I have a speaker. In the other end, I have a gas inlet with propane gas. So I will just ignite it for you. 2 seconds of concentration is needed for me. There we go. That's the Rubens tube. But just lighting a bunch of candles on fire is not that impressive. Or it is kind of impressive, but it's not the only thing that we can do. As I told you, we have a speaker down here, and that speaker can send in single frequencies in this tube. So the first frequency we're going to send in here is 440 Hertz. And almost nothing happens. Great. So now we're going to sweep the frequencies. And now you can see we found a note. In this tube, we now have constructive and destructive interference. In the highs, we have constructive interference, and in the lows, we have destructive interference. So what is going on here is we're sending sound waves propagating through the tube, and when they hit the other end, they get reflected and go back. And when we match it, so the reflections hit the nodes and antinodes of the sound wave coming in, we get this refraction, or not refraction, interference, sorry, going on. And this is always a nice experiment to show because it's quite spectacular. And as you can see, the flames are getting a little bit higher, so I'm lowering them a little bit, just not to melt myself or our microphones. So we can try again. There's a little bit of fire coming out of the speaker. Nothing to worry about. And then we can sweep down and find the next note. There is one here. It's not very easy to see. And the next note, as we're getting lower and lower, the notes are getting more and more difficult to see. But then we go down to the very low frequencies. This is 50 hertz. 30 hertz, and now we're getting a strobe light effect. I don't know if that is showing on the camera. No, it isn't. Okay. Then we're going to...
Now it is. Now it is.
It is now?
Yeah.
Is this showing?
There's flashes.
Yeah, perfect. This is 18 hertz. In this room right now, it's very confusing for the eyes, and we really have a strobe effect. I'm going to turn it off because I really can't concentrate. And that is why when doing, I'm going to turn this off now because I'm melting and everybody's melting in here. And I'm going to go back over here. So especially in a live setting, it's very important to ask your audience before doing experiments like this, if there are any people that have photosensitive epilepsy. Thank you. My English terms are not that excellent. And it's important to take note of your audience always. So if somebody in the audience seems like they're getting sick or they don't enjoy it anymore, doesn't enjoy it anymore, then turn it off and address it. And if it's really bad, they can go outside. And if not, then you can say, okay, now you've experienced it. We are going to try it again for the rest of the audience because one person is not allowed to take the experience away from the entire audience. But you should always weigh that. So every single show is a new experience. And I think every single show is a new experience is my last sentence. So we can take some questions and then that will be the rest of the workshop.
So Miguel asked how many years of experience you have doing this and how you started your company.
Yeah. I have doing these kind of science shows. I have 5 years of experience all the time in university. I'm starting my master thesis now, so I've been studying for 5 years. I was a little slow at bachelor's, so 5 years until my master thesis. So I have those 5 years, but I've always, my entire life, done some kind of performances or speaks or talks and stuff like that, all the way back to primary school. My father is also a physicist, actually trained here at the Niels Bohr Institute. But before that, he tried out to be an actor. So that performance/physics is something I've been raised with my entire life. But it's definitely something that you can learn. I have a lot of friends in the science playground that hasn't done that for that many years at all and are very good at it. So it's something that you can learn. You just have to start. And the question was also, how did I start? At university, I tracked down the first and the best club or environment for this kind of science dissemination, kind of science education, and that just enrolled and spent a lot of time there just to enhance my own skills and doing something that I really find fun and growing as a human. Actually, I really enjoyed it. I think for someone that haven't got the option of joining such a club, then start out by making some small PowerPoint presentations just for yourself, and then doing in front of the mirror, and then doing in front of a friend or a family member, something. Just try to come out with science in some way or another. And you can start with just one single topic for only a couple of minutes, but try to make this bridge that I talked about. I haven't used the bridge euphemism yet, but start low and simple and then build up to something and then go back down and get your audience with you. So a small storyline is quite nice. So that's a way to start. And then just, well, watch some YouTube videos about it and some TED Talks about science dissemination and read about it. This is not something that just is. I know that people are talking about, well, you're really talented about doing this and you've probably done it so many times. I can never catch up with you. That's not true at all. Everybody can do it. It's just a matter of doing it. Many universities has some small experiment sets from the laboratories. Try out with those. Start in the small and then build your way up. And then how did I start my company? Well, in Denmark, it's very, very easy to start a one-person company with low income. It's only 1 Danish kroner, so a seventh of a euro to start a company like that. And then you're registered, and then you can just write out to high schools and primary schools and everything to go out and do talks. So most of my talks are about medical physics that are my own specialty in physics, or science shows or science dissemination. So actually a talk about doing talks. So I have a small collection of talks. I think I have 7 or 8 different options now that I offer, but start with one that you're really good at. Start with something that interests you and just write to people. You don't even need to have a company to start it. It was just easier for me with something as boring as bank transfers. But just go out and try to get some experience. I think that's my number 1 point. Experience. Yeah.
Himanshu asks, did you make the tube yourself? If so, how?
I've made some of the tube, part of the tube. When I enrolled, the primary part of the tube was already built. So the small holes, I can just go in front of the tube again. The small holes were drilled, but it's just pretty much any good quality steel tube. And by good quality, I just mean thick. You need about 1 centimeter or something in thickness to be sure that it doesn't warp or burn in the fire. And then you need a really good seal around the end with the gas, and you need a really bad seal up here with your what's it called? Your microphone? No. Speaker. Thank you. You need a really bad seal, because when you're turning it off, you probably noticed I had some very low flames, and then I turned them off. I extinguished them with a wet cloth. And that was because when the propane isn't being fed into the tube anymore, I can't get the right mixture or the wrong mixture of propane and oxygen, and this is no longer just a nice tube with fires in it, it's a pipe bomb. And building a 2.5 meter, 15 centimeter diameter pipe bomb is not good. So instead of just making everything explode, make a weak point in the end. So this tube will just blow out the speaker instead. So when I'm doing this show, nobody is standing at that end of my tube at no point when it's on. And I don't pass around. If I need to get in front of my tube, I pass the other way around. So that's the safety part of this tube. But a good quality steel tube, and then just bore some holes with, I think we have 3.5 centimeters apart. But yeah, do some small scale experiments first to know the distance that you want. But 3.5 centimeters worked for us. Else you just get a wall of fire instead, and that won't do the note thing. That won't do the interference thing nicely. Yeah. So that's how you build that. And then if a major company in Denmark, such as the main television station, ask if they can borrow it, say no, because when they return it, it's broken, and it took so long to repair it. The Danmarks Radio, which is our main television station, borrowed this, and they returned it broken. The speaker was gone, and there's a membrane in here to make sure the gas doesn't flow out. That was broken, and they ruptured the gas line, and everything was just broken. It took a long time to repair it. Yeah, that's just one of those experiences. Yeah, next question, sorry.
Okay, there was a question before this, but I'm going to ask this first because it's related to the tube.
Yeah.
Does the distance between the holes also change the frequency at which notes appear?
Nope. The only thing that changes the frequency where the notes appear is the length of the tube. So you can use, there is the interference law for half-closed tubes. That is actually what is used here. So yeah, so that is what is used. So go back in your physics books and find the interference pattern for a half-closed tube. And that is the interference pattern for any length of tubing. And then you can just measure out and cut off. But doing so is, you can just take any length of pipe and then you can just change a frequency. That's way easier than having to say that you want a frequency, a note at 280 hertz and then measuring and everything. It's easier the other way around. And it changes every time I use it by 5 or 6 hertz due to temperature changes in the room I'm in, because the length of the tube varies. You know, metal expands in a warm room, and this is a very warm room. So I needed slightly higher hertz than usual. Or low. Yeah, slightly higher hertz than usual. Yeah.
Then Tom asks if you have other science exhibits or sort of setups that you haven't shown that are cool.
Yeah, I do. I have one which I really like, but unfortunately it broke only a few months ago and I haven't repaired it yet. It's 2 microwave emitters that are placed in front of each other, and it sends out polarized microwaves. So you have only one direction of the microwave passing over a small distance, and then you can turn the, not the emitter, the receptor, the receiver, you can turn 90 degrees. And by doing so, you can turn on and off the sound getting transferred by this microwave due to it being polarized. So you can only catch it when it's upright and it turned off when it's at horizontal level, because then the polarization is wrong. But the fun part of that experiment is that you can change that polarization with your fingers. So if you stick your hand in this polarized microwaves and then turn your hand around 45 degrees compared to the polarization, then you can change it. And the receiver can then catch some of the waves, even though it's wrongly polarized by the emitter. I really like that experiment, but unfortunately it broke, and it's a very low volume sound, so I don't think that it would even being a thing that I could show you here. So yeah, that's one of my favorite experiments.
There aren't any new questions, but let's give it 10 seconds.
Yeah, perfect.
Himanshu said it was fun to watch.
Thank you very much. I really enjoyed giving it as well. We're waiting for the YouTube stream to catch up with our real time. So that's the seconds that we're waiting for right now. But if there aren't any more questions, then I want to say thank you very much for seeing this. I really enjoyed giving it to you. I would have loved to have you here in person, so we could have discussed it. But yeah, this is science shows for me. And if you want to ask me any questions about it, you can email me. Is that remotely readable? If not, I think it might go out in the chat right now. Perfect. Yeah, so feel free to email me with questions about how to do these science shows. I would love to answer any, if not all, questions about it. I really enjoy it a lot. So yeah, thank you for your time. And with that, I think we should go to the jingle once again.
It's the time of the year to get together. Sadly, this time around virtually. Let's make the most of it, we always do. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this so long. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's take our time to gather all the knowledge. Brilliant speakers, we share it just with you. Collaborations, friendships, and so much more. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this for 2 years. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's get to it, it's gonna be fun. ICPS. Hooray!
Hello, everyone. We just had a bit of technical difficulties connecting for the next speaker, so we will be postponing 5 minutes. So 5 minutes passed, and we will start the next speaker. Thank you very much.
It's the time of the year to get together. Sadly, this time around virtually. Let's make the most of it, we always do. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this so long. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's take our time to gather all the knowledge. Brilliant speakers, we share it just with you. Collaborations, friendships, and so much more. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this for 2 years. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's get to it, it's gonna be fun. ICPS. Hooray!
Hi everybody and welcome to the next guest lecture. I'm here with Charlie Marcus. He's the director of the Microsoft Quantum Lab here at the University of Copenhagen. So here you go, Marcus.
Thank you very much. When I was asked to give this lecture and told in particular that I had the choice of giving it online or coming over to Auditorium M at the Niels Bohr Institute, I was very excited for the prospect of a live audience and that you had all come to visit Copenhagen and were busily wandering through the city and seeing all of these great physics sites. Well, we'll have to save that for another time. I'm giving a slightly unusual lecture today because I think when you think of Copenhagen and you think of physics, your attention immediately turns to Niels Bohr and the Niels Bohr Institute, and also the history of the so-called Copenhagen interpretation of quantum mechanics. The city is linked with, forever, quantum physics. Interestingly, though, this anniversary of the establishment of the Niels Bohr Institute and nearly the centenary of Niels Bohr's Nobel Prize in Physics, it also happens to be the 200th anniversary this year of the discovery of electromagnetism by, if you didn't know, Hans Christian Ørsted in Copenhagen. So the history of Copenhagen as a center of physics dates back not 100 years to the story of Bohr, but 200 years to the story of Ørsted. And I wanted to start my talk today with a connection from that 200-year anniversary to the physics of quantum mechanics and Niels Bohr, through to today, to the development of a hybrid between electricity, magnetism, and quantum physics, namely the development of a quantum computer. So that's the outline of my talk today. I'm going to start with Ørsted and hopefully end with quantum computing. What was it that Ørsted did? Well, 200 years ago, he discovered that if he ran electricity through a wire, that it made a compass needle move. And he dedicated the rest of his life to demonstrating this. And well, he had a lot of other interests, and he was a writer and traveler and did all kinds of important contributions to science and the dissemination of science. But his principal scientific accomplishment was the discovery that there was a relationship between electricity and magnetism. And that was a phenomenological discovery in the lab. There's a picture of Ørsted in the process of discovering it. And there, in fact, is Ørsted's original apparatus where he would generate currents strong enough using those batteries to make the compass needle there situated below move. Now later, and I'm sure all of you in your classes have studied the right-hand rule for how a magnetic field goes around a current, but at the time, this was just an experimental discovery. Now, what we know is that that experimental discovery set off a unification, and that unification is really one that carries through to the standard model of today, namely that forces in the universe that seem unrelated to one another, in this case magnetism and electricity, are in fact manifestations of the same phenomenon. This was for the case of the simple case, let's say, of electricity and magnetism, finally brought together in the famous Maxwell's equations, also in the 19th century. where the relationship between those fields was finally unified. Now, if you were in Copenhagen right now, you'd see this phenomenon everywhere you went. This thing, which for those of you who are not Danish, I can tell you as an American living in Denmark, I hadn't seen one of these things until I moved here. What you're looking at right now, for all of the Danes, you would say, oh, of course I know what I'm looking at. But for those of you who don't live here, maybe that's a weird thing. Well, I'll tell you what it is. It's a bike light, and it goes on the back of your bicycle. There's also one in the front. And what you can see is that there are magnets that are attached to the spokes of the bicycle, and they go around, and they're at roughly the radius of the bike light. And every time they pass through the bike light, they charge up the battery. There's a battery inside. And they are taking advantage of the fact that dB dt is proportional to E, and that generates a current in the bike light that charges up a battery and makes the light-emitting diodes in the battery glow. This little problem of a magnet and a coil moving past each other, something on the back of every bike light in Copenhagen, was the subject, in fact, of the next great insight in physics, which now takes us into the 20th century with Einstein. But it was the phenomena of Maxwell's equations that led Einstein to his famous first work in the miracle year of 2005. 1905. And it's interesting because I don't know whether you've read it before, but the idea of the paper can just be read. So we can just read Einstein's paper and see what was the issue. And what you'll see is that he was worried about that bike light. It was the bike light that got this whole revolution known as relativity started. And I'll just read you the first part of it, or you can read it yourself on the screen. It's known that Maxwell's electrodynamics, as usually understood in the present time when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomenon. Take, for example, the bike light. It doesn't say that. Actually, that was a misreading. Take, for example, the reciprocal electrodynamic action between a magnet and a conductor, the bike light and the coil. The observable phenomenon here depends only on the relative motion of the conductor and the magnet. Now, we know that, of course, to be true, that all that matters is whether the bike light is passing the coil. It doesn't matter whether the coil is passing the bike light or the bike light is passing the coil. It's the relative motion of the conductor and the magnet. Whereas the customary view draws a sharp distinction between the two cases, in which either one or the other of these bodies is in motion. If, for the magnet is in motion and the conductor is at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy, producing a current at the place where the parts of the conductors are situated. That's how I described it. But if the magnet is stationary and the conductor is moving, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force, which in and of itself, there is no corresponding energy, but which gives rise, assuming equality of relative motion in the two cases, that is, if this is moving this way, then that one's moving the other way, to electric currents of the same electric forces in the former case. Examples of this sort, and I'm not going to keep reading the text of Einstein's paper, but examples of this force, together with no apparent relative motion of the light medium, that is the ether, suggests a new set of laws, which I'll underline here for you. That the laws of electricity and electromagnetics and optics will be valid for all frames of reference, and that light always propagates in empty space with a definite velocity, and that what Einstein said in 1905 was, let's just assume that. So maybe you were wondering, where did this speed of light is always the same come from? And the answer is, Einstein said, let's assume it, just for fun. Let's assume it and see what happens. And what he discovered is that those two postulates suffice. Number one, that the laws of electricity and magnetism are valid for all frames of reference. And number two, the speed of light is constant. And what comes out? Everything. all of Maxwell's equations, the whole story comes out using only those two postulates. So that was 1905. And you might think, well, that's it. That kind of solves the problem. But it doesn't. There were other problems going on in physics that this didn't address. The unification of the forces was not all that was going on. Let me raise one which is not probably one that you hear all the time, but which again comes back to Copenhagen. This is a picture of Peter Zeeman, Dutchman, who discovered how, when you put a flame in a magnetic field, the color lines of that flame split in a magnetic field. And in no magnetic field, you see that the colors of that flame produce a series of sharp lines. And when they are split by an applied magnetic field, they split into some number of, again, very well-defined lines. This was Zeeman's experimental discovery. The problem was they split into the wrong number of lines. You couldn't figure out why, for a given atom, why on earth the lines would split into that number of lines. And it remained a big mystery. There's a famous quote here you see from Wolfgang Pauli sitting here with Bohr at the Niels Bohr Institute, recalling a quote from 1946 that he made for 1923 at the time. A colleague who met me strolling rather aimlessly in the beautiful streets of Copenhagen said to me in a friendly manner, "You look very unhappy." Whereupon I answered fiercely, "How can one look happy when he is thinking about the anomalous Zeeman effect?" So this was really troubling all the way into the 1920s, that the brightest minds in physics were still deeply puzzled by the problem of the Zeeman effect, and you'll see where it leads. About this same era, 100 years ago, at the beginning of the Bohr story, an experiment was done by two German physicists named Stern and Gerlach. And at the time, what the Stern and Gerlach experiment showed was that if you place a spin system, which wasn't known at the time, in a magnetic field, that rather than splitting up into a big blob, as I don't think my mouse works. Maybe you can see my mouse. Let's see. Can you see my mouse if I do that? Yeah, that's great. Rather than splitting up into a big blob reflecting the possible orientations of that spin in the magnetic field gradient, it split up into two equal blobs that went into this. That was not understandable. But nonetheless, Stern and Gerlach, or Gerlach in this case, wrote a postcard to Bohr. Here's a picture of the postcard that he wrote to Professor Niels Bohr. I guess if you're that famous, you just write Professor Niels Bohr, Copenhagen. That's all you need to write. And it said, "Attached to the experimental proof of directional quantization, we congratulate you on the confirmation of your theory." Now, reading forward a little bit, life gets to be more complicated. Here, sitting at the Niels Bohr Institute, and sorry for those of you who are not here today, because we could just go right over to that auditorium, which is still in use today. And for those of you who are here in the live audience, this is probably a place where you've already had classes. But here, sitting in the front row, is a young man named Ralph Kronig. Probably you may not have heard of. That's right. Ralph Kronig was one of those geniuses lost in history. Not completely, but somewhat. Ralph Kronig said, "I think I have an idea. What if those electrons carried intrinsic angular momentum that you could call spin, like a planet spinning on its orbit, not just orbiting the sun, but spinning on its orbit? Wouldn't that both explain the Stern-Gerlach experiment and the anomalous Zeeman effect?" I'm going to go ahead quickly to see whether I show this. Yes, okay. So the story of Ralph Kronig, unfortunately, was that he passed this idea off to his thesis advisor and to his colleagues around and said, "I have this idea." And they said to him, "That's the stupidest idea I've ever heard in my life. Don't publish that idea. You'll make a fool out of yourself." So it turns out that two young graduate students in the Netherlands published that idea first, Goudsmit and Uhlenbeck, and they got all the credit for it. But interestingly, you could ask yourself the question, so who got the Nobel Prize for the discovery of spin? Spin. The answer is nobody. Because everybody knew Ralph Kronig had done it first, but he never published it. Just put it in a drawer and put it away. I'm not sure if there are larger lessons here for you in the audience about following your own ideas and not listening to your advisors. But the trouble that this spin business led to is something that I'd like to carry forward. Here's a picture of Bohr and Einstein in discussion in Copenhagen. And what you can tell from the expressions on their face is something's obviously bothering them. And what was bothering them was something that was already intrinsically in the Stern-Gerlach experiment. I showed you this slide already in the postcard from Stern and Gerlach congratulating Bohr on his theory. Bohr wrote back the following quote. This is what was bothering him and Einstein at the time. Bohr wrote back and said, I would be very grateful if you or Stern could let me know in a few lines whether you interpret your experimental results in this way, that the atoms are oriented only parallel or opposite, but not normal to the field, as one could provide theoretical reasons for the latter assertion. Meaning, wait a minute. You asked the spin a question. Are you pointed up or down? And it answered the question. Some said I'm pointing up, and some said I'm pointing down. But what if the apparatus had been turned sideways, like this, and you had asked the spins, are you pointed east or west? They would answer. Some of them would say, I'm pointed east. Some would say, I'm pointed west, and they would go into those two blobs. How did they know what to answer? Do they have on board the information that says, if you ask me this question, I'll answer that. If you answer me this question, I'll answer that. If you ask me this question, I'll answer that. If you ask me this question, I'll answer that. If you ask me this question, I'll answer that. An infinite number of possible questions because there's all kinds of angles that they could ask. And as we know, if you were to subsequently ask the spin, are you pointed up or down, it will answer, and then it will give a random answer to the next question of, are you pointed east or west? Is the information on board the electron? If the information is not on board the electron, where the hell is it? How does the electron know how to answer the question? Does the electron contain the answer to the question before the question is asked? Or once you ask the question, does that force the electron to make up an answer? In other words, God is playing dice with the universe. God is saying, when you get to here, the answer that you give will be random. And Einstein said, that doesn't make sense. That there's a random answer to a question that was not known before it was asked. Surely an electron, like any other physical object in the universe, knows in its own heart what it will answer when asked a question. It surely couldn't depend on the question itself. And that is what was bothering these two men. And that is the revolution of 20th century quantum mechanics. Now, this sat as a conundrum for the next 15 years or so until 1935. Now, you might think when I'm going to say when it was resolved. No, it wasn't resolved in 1935. It got worse in 1935. Here's a picture of Einstein in 1935. He's getting kind of older now. And he wrote a paper with two colleagues, Podolsky and Rosen, that said, we've got really serious problems here. Worse than the fact that the Stern-Gerlach machine didn't know how to answer the question. What if we take as an example the case of a spin singlet, like the ground state of the two electrons in a helium atom, one's pointed up and one's pointed down. And we know that one is pointed up and one is pointed down because the ground state of helium consists of two electrons that must fill the shell, taking advantage of the opposite spins that Uhlenbeck and Goldschmidt and Kronig had discovered that resolved the anomalous Zeeman effect. So we know that they're in a singlet state. Remember, it's 1935 by now. So now separate the two and instead do your measurement on this one. Ask this one whether he's pointed east or west. And that one will know the answer. That one will know that if this one answered east, he must be pointed west. Or if you ask this one if he's pointed up, this one must be pointed down. Now, what if you've let them separate halfway the distance of the galaxy? Then all of a sudden, when you measure this one, that one instantaneously, remember that's Albert Einstein with relativity. That's Albert Einstein says nothing goes faster than the speed of light. This one instantaneously knows the answer to the question. It instantaneously knows at the other side of the galaxy whether it's pointed east or west. Something's wrong. Something's wrong with the world or our view of the world. 1935. In the modern language, you talk about two detectors and helium atom, and this is what I just talked about. But in 1935, Bohr responded to Einstein in a paper, single author, with the same title as Einstein's original paper. It said, "Oh dear." And what he answered roughly was the following. You can look up the paper. Niels Bohr, Can Quantum Mechanical Description of Reality Be Considered Complete? Is, that's the way it is. Stop imposing your view of the world on the world. Stop telling the world how it has to be. Just open your eyes and look. And he quoted in this paper, "In fact, this new feature of natural philosophy means a radical revision of our attitude as regards physical reality." That is, yeah, the world that we think we're living in which not only do objects have properties before you measure the properties, but correlated measurements don't instantaneously transmit their information, is not the world that we actually live in. We live in a world in which this kind of stuff happens. And we imagine a different world because our brains evolved in a simple way so that we could get food and survive, but it's not really what's going on. Wow, that's quite a world to be living in. That was 1935, and there was a lot of debate afterwards. And it wasn't until the mid-1960s that another name that you probably know, but may not know the whole story of, John Bell, said, you know, this question about if you measure this one and it automatically determines that one, and if you ask it east and you determine it west, that actually can be done in an experiment, you know. And you can actually find out whether or not that information was on board the electron, whether or not those two electrons had said to each other before we leave, listen, if he asks you about west, say you're west and I'll be east. And if he asks you about north, you say north and I'll be south. And that they had conspired to answer every question previously. You could find out experimentally whether or not that information was on board the electron. And as John Bell quotes here, from the famous Bell inequalities that you've probably heard of, I don't know of any conception of locality. Locality means that the information is on board the electron. I don't know of any conception of locality which works with quantum mechanics. So I think we're stuck with non-locality. I think we're stuck with the idea that the measurement on this side of the galaxy does determine what happens on that side of the galaxy instantaneously. Now, experiment is the arbiter of truth. And so in the subsequent decades, Bell's idea of experimentally testing whether or not this notion, known now from the term from Schrödinger in 1935, also called entanglement, was a real phenomenon. And the experiments all came out the same way. And they continue to this day. So now here from the New York Times, 2015. Sorry, Einstein, quantum study suggests spooky action. The spooky action at a distance that Einstein referred to is real. Well, we didn't have to wait until 2015 in order to do that because it had been done many times since then. But I can tell you what was going on in this experiment was the beginning of something that I'm going to turn my attention to now. You see, the folks who did this experiment were at Delft University in the Netherlands. But it's important, and probably there's some people from Delft online here. It's important to recognize that this is Delft University of Technology. This had already made the crossover at this point. And why was Ronald Hansen and his team carrying out this experiment? Not to once again check whether Bell's experiment was correct or not. I think that was already established fact at this point. But rather to start asking the question, sure, it's weird. Sure, it's hard to understand. Sure, it's seems like it's wrong. But let's say it's true. Is it good for anything? Is there anything we can do with that information technologically that some door has opened to our recognizing that the world is a more complicated place than we might have originally thought? Is that of technological relevance? And what I can say, and what's true there too, is that that little bit of quantum mechanics is not built in to any of the uses of quantum mechanics, from the LEDs in the bike lights to the computer chips that you're using today, all of which, of course, it goes without saying, are quantum mechanical objects, because everything's a quantum mechanical object. But that little bit of quantum mechanics, I make a measurement here, it determines an outcome over there, is not used. It's not part of any technology that we use today. It's not part of how an LED works. It's not part of how an MRI system works. It's not part of how a computer works. It's simply unused. We haven't figured out good ways to use it yet. This is the beginning of that, beginning of the applications of those ideas. So let's pretend we want to build a computer that takes advantage of those ideas. And we want to talk about the bits inside of a computer, but we want to talk about them in a quantum mechanical language. So I'll put them inside of ket operators so that they look like they're quantum mechanical objects, or I'll label them with arrows pointing up and down, which does not mean that I want to call them spins in the sense of traditional spins of the angular momentum, intrinsic angular momentum of objects. Rather, I use the notation of arrow up or arrow down, or 0 or 1 in kets, or a light switch in the up position or the down position, to suggest that this is, and this is important because I think people, when they see spin notation, they think that this is kind of fancy. This is the opposite of fancy. This is the simplest quantum mechanical system that can show these effects. It's just two possible states. So it's not all the positions in space, which is an infinite dimensional Hilbert space, if you want to call it that, a vector, infinitely long, because you could be in any one of these possible locations. And so you have to have the vector describing your location be infinitely long. What's the simplest quantum mechanical problem you can write down? It is, you can only be one of two states. They could be different in location. They could be here or there. That's all you can be, here or there, or up and down, or spin up or spin down, or on or off. That's the simplest quantum mechanical problem you can write down. And already you're going to see that life gets complicated. So what quantum mechanics tells you is that until a measurement takes place, which projects the state of this simple two-level system onto switch up or switch down, you have to write down a superposition of those two states, which could have weightings. And the weightings, when squared, tell you the probability that it gave a switch up or switch down probability. So that's the simplest version of this complicated world that we live in now. So now let's imagine that instead of a spin up or down or a switch on or off, it was whether or not a transistor was energized or not energized, by which I mean whether there was charge on the capacitor of a field effect transistor that opened the field effect transistor that let electricity go through. So that's how the little chip works. But we can just call it a 0 or 1, like a bit in a computer, a bit on your memory stick, and ask the question, if I have a transistor which is in a one state, and I make it in part of this Einstein-Podolsky-Rosen entangled state where I say that there's another bit somewhere else, and its state is linked to the state of this one, like maybe the electricity flowed through the capacitor on this transistor and charged up as it flowed through another capacitor. So that that one was on, letting electricity go through, would charge up this capacitor and turn that one into also an on state. And then that turns on the transistor somewhere else. So that means that if I measure this one, that one knows what its answer is. But they're remote. They're on far sides of the chip. The information about what state this one's in determines the state that that one's in. Then that transistor would be, when you measured this one, if this one was opened, instantaneously become closed and let electricity flow through it, which would charge up something else on the other transistor. Then that one would be linked to this one. So when I measured this one, it would not only determine that one, it would determine the other one. Now it can get interesting where this one goes back to the first one. And now multiply that by 1 billion or so transistors on the whole chip and have every one entangled with every other one. What on earth would that do? And the answer is, nobody knows. Nobody knows the power. Nobody knows the limitations. Nobody knows which problems that would not be able to address in a computational sense. And nobody knows which problems it would be able to address in a computational sense. And nobody knows how to build it. That's 2021. That's where we are now. There has been an incredible amount of work in this subject called theoretical quantum computing, which asks questions like, okay, here's a hard problem. Here's a problem that I want to solve. How does this protein fold? You know, take a problem that's of practical value. What kind of molecule would make a binding agent that would trap COVID? What kind of material would superconduct at room temperature? These are questions I'd like the answer to. Could that machine answer that question? Don't know. You could wishful thinking, you could say, oh, it's so powerful, surely it can answer that. But that's not, that's not, scientists don't work like that. Scientists say, we have to figure out what class of question that is, what problems are those similar to, and what problems can a machine like this probably address, which kinds can it probably not address, and where is that problem in this class of problems? And I'll get to some examples in a minute. Then comes the problem of how do you build it? And now this is interesting because we happen to be living in a really interesting time right now where there are alternative approaches that really don't look very similar to each other. They all have the property that their constituents can be in one of two states, like a bit that can be on or off, 0 or 1, and that if you don't disturb them, they'll tend to remain in that quantum mechanical superposition for a long time. That is, you can interrogate them and find that, for instance, depending on how long you wait, they'll give you a 0 or a 1 or a 0 or a 1, suggesting that they're in the superposition state. And I've listed 3 of the interesting competing technologies now, and one of them has to do with atoms, and these are ions, meaning that you've taken some of the electrons off of the atom so that it has a charge. But it means you can hold it in an electrostatic trap because it's charged. And you can look at the energy levels, and the energy levels might be, you knock the thing up to some energy level state inside, and you either knock it up into this state or you knock it up into a state nearby it. Okay, good. That's a perfectly good 2-level system. This one or that one. That's the 2 states. Superconductors carry electricity without dissipation. So if I make a loop of a superconductor, I can put electricity in it, and I could say, for instance, that the electricity is going clockwise and counterclockwise at the same time. Now, the counterclockwise generates a magnetic field, as Ørsted taught us, where you go like this with your right hand and it tells you that it makes a magnetic field and you can measure it. Which means that until you measure it, it's going this way and that way at the same time. And there's a whole universe of researchers, including those at IBM and Google, who are investing in this superconducting technology. Then there's also, and this was something that I worked on 20 years ago, using the actual spin of Kronig and Lindbeck and Goudsmit to be the 2-level system. that the thing could be spin up and spin down at the same time. And then you could read out, again, its magnetic moment or its interaction with other spins using these kinds of technologies. These are all sort of nano-fabricated devices that are able to hold a system in a two-level state until it's measured. And now, finally, 3/4 of the way through my talk, this is the business that I'm in. And which one of these do I do? The answer is neither. I'll tell you about what I do. It's a little different than all of these. But I want to tell you about the most common one, that if you read what Google is doing, or you read what IBM is doing, or you read what other companies or laboratories or universities around the world are doing, I'll just tell you what the two-level system is that they're interested in the superconductors. I said that I sort of made it a kind of a cheap version, clockwise or counterclockwise current. I'll give you a little bit more information. Here are 3 problems that you've probably studied in your studies now, and I think that you probably know the deep analogies between the first 2, but maybe not yet studied the deep analogies with the third. So I think that most of you know that if you write down an LC circuit, it looks like a harmonic oscillator, and you can make a mapping between a mass on a spring that moves at some frequency and an LC circuit. And the C plays the role of the potential energy, and the L plays the role of the kinetic energy, and you can look at the second order differential equation and see that that second order differential equation is the same between the two, with just different terms playing different roles. And you probably also learned in your mechanics class that for small angles, a pendulum is the same as a mass on a spring. Again, if you make the approximation that sine x equals x for small angles, then you get, again, a linear second order differential equation whose solutions are periodic motion, and they look the same for small angles on the pendulum. But when the pendulum is big, you know, like it's almost risking going over the top of the pendulum, then that doesn't look at all like a harmonic oscillator. In particular, a pendulum can go over the top, but a mass on a spring, there's no top for it to go over. So that's where the analogy breaks down. It's only the same in the small angle approximation. But there is an electrical version of the actual pendulum, including the fact that it's a cosine potential instead of a linear potential. It's the restoring force is not kx, F equals minus kx for a spring, but it's k sine x for the pendulum, because it's the projection of gravity pulling down. And the analogous object is shown here. It's not an inductor. It's called a Josephson junction. And that junction is something which is made out of superconductors. And it makes the electrical analogy of a pendulum. Now the quantum mechanical version. The quantum mechanical version of the harmonic oscillator, which is what both of these two on the top are, is the problem of a harmonic oscillator in quantum mechanics. And I suspect that most of you have taken the Introduction to Quantum Mechanics course, and you've learned about ladder operators. And if you used Griffiths, there was that great picture of the cat climbing the ladder, and the cat is climbing the ladder, and you see that the states are equally spaced. That you have raising operators and lowering operators, and that was the solution of the harmonic oscillator problem in quantum mechanics. Now, let's look at the pendulum problem. And remember, the potential is a little softer than the potential of the harmonic oscillator. It bends out at the ends. That's the pendulum getting soft as it gets to the top. And it gets so far to the top that it can go all the way around, meaning that this potential is a cosine, not a parabola. Now, of course, as you know, a cosine is very much like a parabola at the bottom. 1 minus cosine is like a parabola at the bottom. But it softens up at the top. And what that means is that the levels are not equally spaced. It's not a harmonic oscillator level. The rungs of the ladder that the cat is climbing up are not equally spaced. That's the magic. Because if I want to make a two-level system, I want to be able to put radiation on and drive it between two states, and I don't want that third state getting involved. So if the third state is a different spacing, it won't get involved. And only these two states, which I'll call ground and excited, will be involved in the pendulum, because it's a nonlinear pendulum. That's the magic. That's the qubit. That's the two-level system. That's what those guys are doing. So here it is, slightly more detailed. Where do you make a Josephson junction? You make it using aluminum. You put an oxide in between. The electrons can tunnel through the oxide, and in so doing, make this non-parabolic two-level system that can form a qubit with those energy states. And they have all kinds of ways of keeping it secure and on a chip. It is worth mentioning that all of these things all use aluminum, which was first identified by Hans Christian Ørsted in 1895, again, bringing this technology back to Copenhagen. And here's an example of the two-level system that this thing forms, here read out by how long you wait to see whether it's a 0 or 1 or a 0 or 1. And what you can see from these data is maybe the answer to the question of where does our classical world come from? Because you can see that hard as we try, we can only get that thing to stay in a two-level system of superposition of 0 and 1, or up and down, or clockwise or counterclockwise, or the ground state or the excited state, for about 50 microseconds. Now maybe it's up to 100 microseconds or something like that. But after that, it's been measured. By whom? By the world. The world finds out what state it's in. It's that time, how long you can preserve the superposition, that tells us whether or not we're going to be able to build one of those quantum mechanical machines or not. And look what's happened. It's kind of like the Moore's law of electronics. Look what's happened to that characteristic time between just the 15-year period between 2000 and 2015. That time has gone from nanoseconds to microseconds to hundreds of microseconds as that time has gone on. Still not a long time, but in comparison to how quickly you can operate transistors inside of a chip, which usually have gigahertz clock speeds, 100 microseconds is like an eternity. 100 microseconds is orders of magnitude longer than the characteristic time that it takes to do all of these manipulations inside of a computer. Great. So we've crossed some threshold where you can make the quantum mechanical state last a long time compared to the other state. And in fact, this was announced in the last year from Google in 2019 that they had built a chip with 53 of these transistors on it that were in the superposition of state, and they're in the process of using this thing to solve quantum mechanical problems. Here was the chief engineer of that, visiting Copenhagen, climbing up the twisty tower over on the other side of town, that if you were here in Copenhagen, you yourselves could go climb. That's John Martinez, who was the designer and builder of that system. I work for Microsoft in addition to being a professor at the Niels Bohr Institute, and Microsoft is taking another way up the mountain. And I want to tell you about that. I realize that the time is flying. I've got about, tell me what time I'm supposed to stop talking.
You can do 25 minutes
More?
and
Okay.
then the QA session afterwards.
Okay, let's see what I can do to see how far I get. The route that Microsoft is pursuing is different than the route that Google and IBM are pursuing, and I want to tell you about that route now. It's extremely interesting, and I dare say beautiful. Here's where the idea starts. The idea starts with the idea that if I want to look at, say, a piece of rope and decide whether or not it's tied in a knot, if I can only look locally at the rope, it's pretty hard to tell. You have to kind of zoom out and see what other parts of the structure go in and around. If I can only look at a little piece of rope, I can't tell whether it's tied in a knot. Which means if I'm in a world in which the environment is probing the sample locally, and I can figure out how to take a quantum mechanical wave function and tie it in a knot, I may be able to hide the information from being measured by that kind of an environment. I want to be able to encode information in a topological space where the topology is hidden from environmental measurement. And this was something that was predicted mathematically, theoretically, and it was found that, in fact, such a system can exist and would be immune from decoherence. It would be immune from the measurement problem insofar as measurements are local measurements. That's the beautiful idea. Here's a picture of Michael Friedman, a Fields medalist, mathematician, and one of the architects of this original idea of how to make a topological quantum computer. He's also a bit of a mountain climber and rock climber, so here he is in Copenhagen getting himself in some kind of trouble down by the harbor, climbing on something that he probably shouldn't be. But Mike and these other architects were key to turning this idea of measurement immunity through topology into a scheme for computation. And again, this is now about a 20-year-old idea that says a qubit made by topological encoding would be immune to decoherence. And that's such an attractive idea, given that even though 50 microseconds is pretty long, it's not that long. And maybe building something from scratch that's immune to decoherence is a better way to start. This idea of topological encoding of information in a quantum mechanical system sounds exotic, but in fact, this was the subject of the 2016 Nobel Prize in Physics. And if I read to you from the Nobel webpage, topological insulators, topological superconductors, topological metals are now being talked about. These are examples of areas which over the last decade have defined frontline research in condensed matter physics, not least because of the hope that topological materials will be useful for a new generation of electronics and superconductors, or in future quantum computers. So that is the motivation, and here's how it works. It was discovered in 2010 that a particular material system could produce excitations that would have the property that the information would be stored in a non-local topological way. And the best analogy I can think of for this is one of those necklaces in which the words are written, you know, best friend, I love you, whatever. And then you give one to your boyfriend or your girlfriend, and they have half and you have half. And the only way you can read it is to bring the two halves together. And that's the idea for this form of topological quantum computing. And the idea was the following. If you take a one-dimensional wire and the word is proximitize, from the word proximity, which means nearness. If you proximitize the wire to become superconducting by just putting it near a superconductor, the wire will pick up superconductivity. And in the presence of two other features, an externally applied magnetic field and something called spin-orbit coupling, which is that the spin is coupled to the motion. When the spin is moving this way, it thinks it's in a magnetic field aligned. When it's moving that way, it thinks it's in a magnetic field moving anti-aligned. This coupling between motion and spin exists in materials. Maybe I should just say why this notion of spin-orbit coupling exists in materials. And the answer is Einstein, relativity. If there's an electric field inside of a crystal and I'm moving in an electric field, what do I perceive? I perceive a magnetic field. But if you remember, Einstein would say that the magnetic field that you perceive by moving in an electric field depends on your motion and the motion of and the direction of the electric field. From Maxwell's equations, you're moving in an electric field, so you perceive a magnetic field. And if you move the other way, you perceive the opposite magnetic field. Perfect. So all you have to do is run in a crystal that has an electric field. And if you're running in a crystal that has an electric field, you get spin-orbit coupling, plus an external magnetic field, plus proximity effect in the one-dimensional wire, and you're done. You get these excitations, and the excitations will be topological, and the information will be held in a non-local way. All you got to do is make it. Here, in fact, is Mike Friedman sitting in Copenhagen with our condensed matter theory team. Here's Carsten Flensburg at the blackboard, working with Mike to take the theoretical ideas in the mathematics of topological quantum computing and turn it into how do you build it in the lab? What's the material you use? What's the temperature you need to run at? How big of a magnetic field do you need to apply? Do the materials have enough of a built-in electric field that you can use them? The semiconductor materials that produce the spin-orbit coupling and make the one-dimensional wires are grown here in Copenhagen. They're also grown in several other labs. Lund in Sweden is a great place where they grow these kinds of wires, and many labs around the world have them. I happen to be showing you a picture from the Copenhagen lab where we grow these nanowires. The material is listed at the top there as indium arsenide. Those are two materials from the third and fifth column of the periodic table. They form a beautiful crystal that has strong spin-orbit coupling. That's the necessary ingredient. It also proximatizes very easily if you bring it in contact with a superconductor. In 2012, following up on the ideas of the invention of this, my friend Leo Kouwenhoven and his group at Delft University built the first system that attempted to take, and I'll show you with my cursor, a nanowire made in this case out of another column 3, column 5 material, indium antimonide, and put it in contact with a superconductor and find out whether or not it had those red balls at the end of it. And what should happen is that the red balls should show up as a zero energy peak as soon as you apply enough magnetic field that you cross the threshold into a topological superconducting state. So it wasn't surprising that these features drew a lot of attention, and these so-called Majorana zero mode states, which are this topological state, was identified for the first time here. In Copenhagen, a few years later, 2016, the group of Jesper Nygaard, Thomas Jespersen, Peter Krogstrup, along with my own team that was doing the measurements, took the next big step and figured out something amazing, which is that under the right conditions, here you see in this picture, you can grow the superconductor in contact with the semiconductor. So there's a picture of indium arsenide, the semiconductor, and aluminum, our favorite superconductor, grown as a single crystal. Now that had never happened before. So now, 2016, we all of a sudden have something that's needed for making this hybrid of proximity effect that's never existed, namely the epitaxy, or the crystalline growth across an interface of superconductors and semiconductors in these nanowires. And now we were kind of off to the races. Let me skip forward, because what happens now is you're kind of modern day in the lab figuring out how to use these new epitaxial materials to try to make the first generation of these qubits to find out whether or not this topological encoding really gives you this extended time over which the coherence is left unmeasured because it's topologically encoded. Probably you want me just to give you the answer. Is it true? Is it true that if you encode the information topologically, that the coherence time diverges or at least becomes very long? Well, here's the proposal to do it, along with dozens of others. And unfortunately, what I have to tell you is, I don't know. I don't know, because I need you all out there to apply to be students in my lab so you can come and find the answer, because we haven't done it yet. It's still an open experiment. The idea of topologically encoding information, which is so solid in mathematics and theoretical physics that there hasn't been any arguments against it, simply hasn't been demonstrated yet. Maybe in a couple of years, you'll have me come back and give a talk about what the answer is. Or maybe you'll give the answer because it'll be your experiment that measures it. But already the ideas are beginning to take shape, and we're beginning to use these nanowires to build electronic devices that look like the theoretical models that show this kind of thing. Now, how do we build such a thing? Remember, I show a 1 micron scale bar on this thing, which means you can see that the dimensions here are tens or 20s of nanometers. Just to give you a size scale, a red blood cell is 8 microns in diameter. A human hair is 60 to 100 microns in diameter. So this entire little device, you could write the thing on a red blood cell. So it's pretty advanced technology just to get started and just to build it. That little device you can see in the left, if you zoom out, fits onto a computer chip. The computer chip fits into a circuit board. The circuit board goes into mounting hardware. The mounting hardware goes into a refrigerator, and the entire refrigerator sits at about 1/100th of a degree above absolute zero in the laboratory. So a lot of work goes into not only the mathematics of whether it should work, the theory of reducing that mathematics to a concrete proposal, the design of the materials, including epitaxy of superconductors and semiconductors, the building through nanofabrication of the devices themselves, the cooling of the devices to 1/100th of a degree above absolute zero, and the measurement of those devices sitting in that cold environment to find out whether they are in a superposition of these now topologically encoded states. And that, finally, at the top of the hour, is the work that we do in the lab. There are other schemes and proposals that get more complicated about how you can build these kinds of things. And one of the advances has been to generalize the wires to two-dimensional systems. I think in the interest of time, I'm going to skip and go forward more or less to the end of my talk. I had lots of other things. Oh, there's one other slide that I want to show you here that I think is important. And that's this one. And then I'm going to skip to the end. This is the inside of one of those dilution refrigerators sitting at 1/100th of a degree above absolute zero. And you remember when I described this chip, this one opens this one turns on this one, this is one, and then they're all entangled with each other. Well, that would be the same whether it's topological or made out of superconductors or made out of spins or made out of atoms. You have to get all these things wired up to each other. How do you do that? And what I want to emphasize is that we're now at the boundary between what you would call experimental physics, experimental condensed matter physics, and straight up electrical engineering. Except it's straight up electrical engineering that has to take place at 1/100th of a degree above absolute zero. But you have to build control electronics to do all of this manipulation, just as if you were building some world's most complicated controller to control a robot or something, and it all has to live at this ultra low temperature and work and control the chip. And this is an extremely difficult problem. And what my view of the problem of quantum computing is that because it resides at the hybrid of, at the intersection of conventional engineering and theoretical and experimental physics, that there really aren't very many people, young people like you, who have an education in both areas. Physicists tend not to know how to use a vector network analyzer and read a Smith chart, and electrical engineers haven't studied quantum mechanics. So there isn't a community of people who are educated to work in this area. And because I happen to catch this audience today at a young age, at the beginning stages of your advanced education, what I can say is that this, to me, is emblematic of the needs for the future. Namely, there's a hybridization going on between the great engineering advances that allow control and fundamental physics and fundamental ideas. And if I could make a recommendation, it would be try as hard as you can to get educated on both sides of that divide, because both sides are critically necessary. I want to show this slide, although I don't think that it's what this is all about. But the world has woken up. Maybe this is all I want to say. The world has woken up to the fact that not only is this a very intriguing frontier of technology meets fundamental ideas, but if some of the problems that can be solved are solvable, it will be a transformation in information technology that the world can hardly imagine. Whether that happens in the next 5 years or the next 50 years, I don't know. I just don't know. I don't know how fast the progress will occur. But at the end, I want to say for inspiration, another hero of Denmark, besides Niels Bohr and Hans Christian Ørsted, is Hans Christian Andersen. And I want to read a little poem or essay from Hans Christian Andersen to end this presentation. Yes, in 1,000 years, people will fly on the wings of steam through the air over the ocean. The young inhabitants of America will become visitors of old Europe. The ship of the air comes. It is crowded with passengers, for the transit is quicker than by sea. The electromagnetic wire under the ocean has already telegraphed the number of the aerial caravan. Europe is in sight. It is the coast of Ireland that they see, but the passengers are still asleep. They will not be called till they are exactly over England. One day devoted to seeing Germany, and one day for the north, the old country of Ørsted and Linnaeus, and for Norway, the lands of the old heroes and the young Normans. Iceland is visited on the journey home. Hans Christian Andersen wrote that in 1853, before the invention of the airplane. It's remarkable. It's remarkable that he was able to see into the future. It's also remarkable that he thought it would take 1,000 years. So while he was a visionary, he got the time scale wrong. It didn't take 1,000 years, it took 100 years. So now we're faced with this prospect that we've revised our view of the modern world. We've encoded information in topological spaces by combining materials that had never been combined before, and now we're trying to turn them into a technology. It's visionary. How long will it take? Probably less time than you think. That seems to be the way things work. With that, I'm going to stop. Thanks.
Thank you very much, Charles. I think there's a bigger applause out there in the world. We're a Sascha group, little group of
it was
people.
heartfelt, and I appreciate it. You could see the sincerity on people's faces.
Yeah, we do have some questions for you. First question, why not make qubits that consist of systems with higher than spin 1/2 so you get more information per qubit?
Yeah, it is an approach, and they have a name. I think they're called qudits or qtrits if it goes into 3 states. And I want to give an answer, I think, which is maybe a little bit technical, which is something like this. Let's say you have a choice between making 10 qubits or making 1 qubit with 10 levels. In one case, the 10 has an advantage which is algebraic, meaning it just multiplies something from 2 to 10. In the other case, making 10 qubits, the number of states goes in the exponent. And so I think that it's not where people have put a lot of time, because if we're stuck with a fixed number and you say, given the choice of suffering the difficulty of making it have 3 states, 4 states, 5 states, 6 states, or just being able to make twice as many qubits, if we make twice as many qubits, with each added qubit, the power doubles. Let me say that one more time. With each added qubit, the power doubles from 53 to 54, from 54 to 55, from 55 to 56. The power doubles. That's a better place to put your effort.
Well, thank you for that answer. I think we'll not be looking into that anymore.
Well, I think that there are people out there, but go look up qudit with a D.
Qudit.
Yeah.
All right. Is it possible that we need to discover new materials in order to keep the qubits in a coherent state?
I'll give you my opinion about that question.
Yes, please.
It's impossible if we don't.
All right.
It's such a fundamental and important question, and it's such a fundamental and important direction for this field to recognize, first of all, even with the little analogies that I gave about crystallization of superconductors and semiconductors, opening up a new door. The materials hadn't been invented before, but even those materials won't be good enough. I think that the frontier of all branches of quantum computing is the frontier of material science.
All right. And then Yeah. So if you say that nobody has invented the quantum computer yet,
No, I didn't say that. You said that.
I said that.
You said that.
Because IBM claims to have some quantum computer, right?
Well, let him take up the issue with you. You're the one who said it.
what is it that they've made?
Quantum computer, I suppose.
But why don't we just use that one?
Well, maybe it's not very powerful.
You can just scale it up.
You can just scale it up. I mean, that's the hard part. Look, I don't want to be giving you a hard time for fun, but there's no definition of a quantum computer. There's no law that says I made something, I can't call it a quantum computer. If I make something with 2, 3 qubits that are quantum mechanical and interacting with each other, or 20 qubits, or 40 qubits, or 1,000 qubits, I think it's a different question. The question is, what problems can I solve with it that I couldn't solve before? Are there problems that I could solve with existing quantum computers that I couldn't solve without those quantum computers? And the answer is yes. I bet you thought I was going to say no.
Yes.
The answer is yes. But now let me change the question again. Are there problems that we can solve whose answers we actually care about that can't be solved without a quantum computer? There, the answer is maybe, maybe not. For instance, the work that Google did was to say, we're going to solve a particular kind of math problem that has to do with random vectors in a space, and nobody cares what the answer is, but we've particularly picked a problem that's super hard for a classical computer and fits right onto our quantum mechanical computer. And the reason we picked that problem is for that reason, not because anybody wants the answer to it. It's a useless question. But now an interesting thing happens. 2 years after that question, someone says, well, actually, I think I can take that question that everybody thought was dumb, including the people who wrote the paper, and turn it into a useful question that we might actually want the answer to. So my question isn't even well formulated about this. It's a useful question. It's not a useful question. So the point of my long answer is these things are not well defined. And what's going on right now is exploring the boundary of our technological capability. And there will be no moment when you cross through something and there'll be a sign on the road that says, you have now built a quantum computer, as you go through it. Maybe we already passed that sign. Maybe that sign doesn't come for another decade. But there won't be a sign on the road. There's just going to be things getting better and better and smarter, and more complicated and more well-controlled. That's the way science works.
All right. I'm not even going to ask you the question about
'Cause
how
I'm too
long time
dangerous,
do you
yeah.
take it will reckon to have a quantum.
Yeah, right, because we just answered that already. It's either a negative number or a positive number or an exponential number or whatever.
Yeah. So I have another question instead.
Okay.
Are there any examples of quantum coherence in nature? If so, how does their decoherence time compares with the ones of lab-made systems?
Yeah, it's a great question. I think that there certainly are. Every chemical reaction you've ever heard of, the conversion of hydrogen and oxygen into water is a quantum mechanics problem. And now you can ask questions like, but what's the coherence time of these molecules? There's a lot of thinking about, is there quantum mechanics in our brain? Do birds use a quantum mechanical singlet triplet pair splitting with reasonably long coherence time in their eye to detect magnetic fields that tell them how to migrate? Okay, so there's a lot of people talking about whether or not there's coherence in biology, whether there's coherence in nature. And the answer is, of course there is. Of course there is. Every chemical reaction in which you talk about covalent bonding is a quantum mechanical superposition of states. The electron is here and the electron is there. There is no such thing as classical physics. There's no such thing as classical physics. All of this is quantum mechanical and all of this requires coherence. Now you can ask a more refined question, which is, are there any examples in nature of coherence times that are very, very long? And the answer is yeah, because for instance, take a radioactive isotope that has a half-life of a year. There it is, sitting as a nucleus. And sometime in the next year, a projective measurement will occur when it will decay. Okay. But up until then, it had the potential to decay. It was unstable, but it hadn't decayed yet. A measurement on it hadn't occurred. Now, in more practical terms, here's another one in which the decay time is about a week, or the coherence time is about a week. There are two kinds of water molecules with the protons aligned. The protons have a nuclear spin. The nuclear spin is either aligned or anti-aligned. Those two things have about a 1 week interconversion time. That's a superposition of two quantum mechanical states, ones in which the two nuclei are aligned, the hydrogen atom, Mickey Mouse with the two hydrogens up here, and anti-aligned. There, it looks just like my qubit, looks just like the Einstein-Podolsky-Rosen, and the coherence time is a week. Can you build a qubit out of hydrogen molecules or H2O, water? Yeah, I think you can. If anyone would like to come and build a water-based quantum computer with a 1 week coherence time, I'll make lab space for you.
All right, thank you. I have one final question for you.
Okay.
So you say you're more, so you have Google, you have IBM, you have Microsoft working on a quantum computer.
Yep.
I was actually wondering how much you share with each other, because I reckon it's a race, right? You want to be the first one to build the best quantum computer.
Well, I think that yes, the answer is yes, and I think that I want to make this, I want to make the subject a little tiny bit more complicated than just that. Here's the picture that I want to show. That's John Martinez. He's Google. I'm Microsoft. But he's my friend. I've known him for years. He's visiting me in Copenhagen. He stayed for a week. We went out, we climbed up the twisty tower, you know. So makes it kind of complicated because all these people, before they were this, we were all friends with each other. Okay, so yeah, probably within these companies, there's probably rules like, listen, don't say exactly what it is that you're working on to somebody who works at the other companies. And we have to navigate, how do we retain our friendships? Then there's the relationship between the university and these companies, which exist. John is a professor at University of California, Santa Barbara. I'm a professor here. Mike Friedman is also a professor at University of California, Santa Barbara, and he also works at Microsoft. And so how do we navigate that space? Well, one thing that I can tell you is that once students are involved, there can't be secrecy, because you can't tell a student, oh, don't put that in your, even though you've made a great discovery, don't put that in your thesis. We don't want the other companies to find out. So when between companies, you know, we're all adults and we all get paid a lot and we can figure out our friendships and how to navigate our friendships along with a little bit of secrecy. It's not that hard. But once students get involved, it has to be another and more complicated game. And the way that that game has to be played is students disseminate information because they're in the sciences and that's what scientists do. And so that required navigating between the universities, and all of these universities are involved. Delft is involved, and the University of Sydney is involved, Copenhagen is involved, Santa Barbara is involved, and there's companies coming out of Berkeley, and there's companies coming out of Stanford, and there's companies coming out of all these places. And the rule is pretty simple. Students, when they have the results, they write it up and they tell the world. That's just the way it has to go. So it's not I don't want to pretend like it's super simple and super easy. It hasn't affected our friendships. I can tell you that. They survive. And it hasn't made any students, as far as I can tell. I mean, someone could write in an email and say that it's not true in my case. I don't think there's any students who are feeling ripped off, who are feeling like someone told them to be quiet. I think that they benefit because a lot of good equipment comes into the universities and they get kind of high-end equipment. The universities benefit because they have a good relationship, or, you know, universities get overhead money from grants that come into the university. And the students who would be potentially ripped off because they would be told this is a secret or that's a secret aren't being told that. I mean, it has to be worked out, but they're not being told that. So I don't think that there's any unsatisfied customers in the whole story. It's just that it had to be worked out. And I think that it has worked out as successfully as human beings are capable of working things out, which isn't always perfect.
No. I would also think that you got a better product in the end if you can share a little bit with each other.
Absolutely. No, I think that that's, in fact, let me just say this. You could say, how could it be that these two big companies with all these smart people working on it are taking different approaches? I mean, shouldn't it be that one approach is better than the other and they come to the same conclusion that they're going to do it this way and we're going to do it this way, and someone else is going to do it some other way? Is some of these companies saying, well, we should be doing it that way, or we should be doing it that way. I think what they're saying is, we're keeping a very careful eye on what they're doing. And on the day they do something a lot better than we're able to do, we'll start doing it their way. We're all reading the same papers. These guys publish this thing in Nature, and they're, people are reading it. So I think that the way the companies are interacting with each other is that they're still publishing, and people still know the answers, and they're taking their approaches because they, at the moment, think that that's the best approach based on the people that are working there. But we're all watching each other, of course. And the universities are doing the same thing. If someone's doing something in university and, pretend you're a graduate student, you're working on some project, and, year goes by, 2 years go by, it's not working. But the person next to you, their experiment's working. I mean, at some point, you're going to go talk to your advisor and you say, could I work on that instead of what I'm working on now? Because that seems to be working better. And that's we would do the same thing. I mean, if something looks like it's working better, you could just pivot and do that other thing. Right now, these are such hard problems that's not the way people are approaching. Right now, they're thinking all of these paths look like they each need some breakthroughs to get over the next hump, but they all look like they're pretty good.
All right, thank you. And thank you very much for your talk. It has been very interesting to hear. And yeah, people are loving your enthusiasm. So keep it that way.
Thank you. Thank you.
And thank you very much, everybody.
Great. What do I do to turn this off now? Do I stop sharing? There we go. Yep. Okay, thanks everyone.
And Charlie, we have a little
Oh, great.
wine for you.
Very nice.
So thank you very much.
Thank you. I hope it was a success. And I
Yes.
hope you every success with the rest of the conference. I hope all of these people out there in the world get to come to Copenhagen.
It's the time of the year to get together. Sadly, this time around virtually. Let's make the most of it, we always do. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this so long. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's take our time to gather all the knowledge. Brilliant speakers, we share it just with you. Collaborations, friendships, and so much more. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this for 2 years. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's get to it, it's gonna be fun. ICPS. Hooray!